Okay, good morning everyone. Welcome to this fourth session on robotics, and thank you for joining this session. We're 5 minutes over time, but I think it doesn't matter because there is a coffee break afterwards. But on the other hand, we shouldn't wait too long neither to start this session. My name is Demeester. I'm working at the University of Leuven. I'm also the session chair. So Leuven is a university in Belgium. Belgium is a country that has beaten England yesterday in the World Cup. Even though that might not have been a good idea, but okay. So this talk is on Clothoidal local path template for intention estimation by assistive mobile robots. It's actually work performed by Denis, a master thesis student. So this work is basically a summary of his master thesis. But unfortunately he left academia for industry and couldn't join us today. But I'll try and convey his research results as good as possible. So let's start off with the motivation behind this work, and that is robotic wheelchairs. So we have been doing, since a couple of years, work towards building a framework for providing navigation assistance to wheelchair drivers, people who cannot drive wheelchairs very accurately. And we focus on the human-robot collaboration aspects in that. For this, we have equipped commercially available electric wheelchairs with sensors, with computing power, and then we added intelligence. Now, what does intelligence mean? For us, we obtain smart robotic wheelchairs if they are able to answer 3 questions. Where am I? Where am I going? And how should I get there? So the answer to the first question, where am I, is given by the traditional localization and map building algorithms that are out there. The answer to the second question, where am I going, is given by what we call intention recognition algorithms. So we don't expect wheelchair drivers to be able to explicitly state to the robotic wheelchair which task should be executed, because it's quite hard and time-consuming for them. But instead they should just try and execute the navigation plan that they have in mind. And it's up to the computer to estimate this hidden navigation plan and then to help the driver. And helping the driver is the answer to the third question, how should I get there? And that is given by shared control algorithms. So algorithms that determine how to share control between the computer and the human driver. Now, in the past, we have adopted a probabilistic framework to estimate these intentions. So basically what we do is we model intentions as geometric paths that the user wants to follow. And these paths are the states that we want to estimate, the hidden states that we want to estimate. And we adopt a base rule to basically generate a probability distribution over these paths. So we generate a bunch of geometric paths, and then we adopt, I don't know if this is working. Should see a pointer, but here it is. So we compute a posterior probability distribution over user intentions I, given past driver steering signals U, and given past other past information. So I won't go into detail here, but the message is actually that a key component in our navigation assistance framework is a path planner. And ideally, this path planner adheres to some requirements, such as it should deal with robot geometry and robot kinematics as accurately as possible. We should be able to generate a whole bunch of paths as quickly as possible and as accurately as possible. Now, in the past, we have used what we call a local path template for this. A local path template of circular paths. In literature, this is also called tentacles. It's tentacles used by autonomous driving cars, for example. And what you see in this figure is a mobile robot localized in an environment, and it generates a lot of forward driving black paths, which are circular, and backwards driving gray paths, which are also circular. And we call it a template because the shape of these paths doesn't change, but we only adapt the length of these paths such that they are collision free. Okay. We were quite happy with this approach because it generated, we were able to generate many paths at a high rate and very accurately. Okay? But the problem that we encountered was that when driving through narrow doors, narrow passageways like doors, we don't find any forward driving paths anymore. And that's a problem because then we cannot estimate intentions of drivers who want to drive through these doors, and we cannot assist the drivers when driving through these doors. So that's basically the motivation for this new research. We like these local path templates, but we are not happy with the circular paths. So we are looking for other shapes that are richer, with which we can reach more goal locations in the robot's neighborhood. And the approach that Kevin followed was the following. It consists of an offline phase and an online phase. In the offline phase, instead of forward integrating linear and angular velocities over a certain amount of time and then getting these circular local paths, we sample the robot's local neighborhood, and these sample points are goal locations, and then we plan paths to these goal locations. And based on these motion primitives, we then construct a lookup table that we can use to quickly check for collisions online. Okay? And then online, we just use these motion primitives. We don't change their shape, but we just adapt their length based on sensor measurements that we obtain or map information that we have. Good. So let's have a look at these 4 steps a bit into detail, or let's look at these steps into detail. So first of all, we construct a local state lattice, a multi-size, multi-resolution state lattice, where we sample the environment at high resolution nearby the robot and at the coarser resolution farther away from the robot. And this provides potential goal locations to which the driver wants to navigate. And then we construct motion primitives to each of these local goal locations, and this procedure is then iterated to get a sequence of motion primitives, which is what you see at the right-hand side. In this particular case, we used clothoidal paths as motion primitives, so geometric curves of which the curvature changes linearly with arc length. They have been used often in the design of railway and highways, and they are designed to generate smooth driving behavior. These clothoidal local paths, or clothoidal tentacles, have also been used in literature by autonomous cars. So we thought this would be an interesting motion primitive to use. So that generates this kind of motion primitives to nearby goal locations, and then if we iterate this procedure, we get sequences of these clothoidal tentacles, which gives us the right figure. Then in a third step, we construct a lookup table. So basically what we do is we have a robot shape, and we let this robot shape follow each of these local motion primitives. And then we check which environment cells are visited by this robot shape. So we also discretize the environment, and we check which cells are visited by the robot when following each of these motion primitives. And in these environment cells, we then store which paths pass through this environment cell and at which position. So these steps are all performed offline, and then in an online phase we can use this lookup table to quickly adapt the path lengths. So here you see an image of all motion primitives that we use online. Basically what we have to do is when we observe obstacles like these 4 dots that you see here, red dots, we transform them into the robot's local coordinate frame, and then we check in the lookup table which paths pass through each of these obstacles, and then we adapt the shape of these paths. So that can be done very quickly. We also evaluated this with our circular local path template. So we used the circular local path template as a baseline algorithm, and we checked it in different scenarios, like a door scenario or a backwards driving into an elevator scenario, which are typical cases with which wheelchair drivers are confronted daily and which are quite hard. Here you see an example of a circular local path finding a solution through a door of an elevator, and this is an example of a clothoidal local path finding a path through the elevator. What we then checked was our goal region is this green rectangle from which starting locations indicated in this red rectangle can we reach the goal location using this circular or clothoidal local path template. And we found out that with this clothoidal local path template we indeed can reach the goal location from many more starting locations as compared to using only the circular local path template. Okay? So in 98% of the cases, the clothoidal local path template could indeed find a path, whereas the circular local path template could only find solutions in 45% of the cases. A second simplification that we used in the past was considering dynamic obstacles or approximating dynamic obstacles as instantaneously static. So we didn't take the future path of dynamic obstacles into account. So a second objective of this research was to check if we have information about the future path of dynamic obstacles, can we also include that in this local path template. In this case, we assume that we have information regarding the future path of dynamic obstacles. So this is an example case where the wheelchair wants to follow this circular trajectory or clothoidal trajectory, and then we have two obstacles, one traveling from right to left, one from top to bottom, and we assume that we know the shape and the position of these obstacles as a function of time. And then what we're looking for is to find a velocity profile of the wheelchair along this path such that we reach the end location of the path as fast as possible, while of course avoiding obstacles or collisions with these dynamic obstacles. How do we do that? We proceed basically in two steps. We first construct a distance-time collision space, which you see here at the right. So this is a space that of which the horizontal axis determines time and the vertical axis denotes the distance along the path. And for each of the moving obstacles, of which we know the motion, we determine which time position along the path combinations yields potential collisions. We do that in two steps. We first create a rectangle, which is a coarse estimate of where there might be collisions between the robot and these dynamic obstacles. And then in the second step, we compute the actual shape of this distance-time obstacle more accurately. Okay. We also assumed some simplifications to make the obstacle convex, so that in the next step we could formulate a constraint optimization problem in this space where the objective to minimize is the time. So we want to reach the end of the path, which is denoted by this green line, as fast as possible, starting from time 0 and position 0 at the path, whereby we avoid collisions with these distance-time obstacles, and where we take the dynamics of the wheelchair into account as well. So we cannot go instantaneously fast from start position to this end location. Okay, and a typical result that we get is this, the blue path that you see here. In this case, of course, the robot is a point in this space. Good. Okay, that brings me to future work. For us, this path planner is just a tool that we want to integrate in the navigation assistance framework. So it would be interesting to get some feedback from path planning specialists as you to get some advice about alternative approaches. We realize that there are still various tracks for future work. I'm just mentioning two of them here. One is that we want to deal with the intelligence of dynamic obstacles. So what we did now is we assume that we know the motion of these dynamic obstacles and that this motion doesn't change with respect to the actions that we take. But in reality, of course, obstacles are intelligent and they also see what we're doing and they react to it. So that interaction behavior should still be included. Second thing is, we like these local path templates, but still it generates only a limited set of local path sequences, or the number of action sequences that we can get out of it is quite limited. So we're thinking of using a local path planner, either deterministic or probabilistic, that can generate much more complex action sequences, such as parallel parking, for which we also want to provide navigation assistance and estimate intentions. So, of course, when we would adopt these planners, that means that we have typically to discretize action and state space. And that brings us back to the original problem where if we use the exact robot shape and we want to drive through a narrow passage, if we discretize state and action space, we might not find solutions to go through these narrow passages. So we're thinking of finding ways to easily approximate robot shape and path shape on the one hand, and also state transition functions, so that we can use a coarse state and action space discretization while still finding paths through these narrow passages. That's the idea. So we're experimenting with that. And with that, I'd like to thank you for your attention, and if there are questions, I'm very happy to answer them. Yes. From here, I'll try. Okay, perfect.
Hi. Really nice talk. And I have a question about these clothoids and the state lattice created with this. Because the issue with state lattices is that curvature is not continuous on the nodes of the lattice. So with these clothoids, are you able to construct path which is continuous in the sense of curvature of the path?
We didn't use, so we use the toolbox to compute these clothoidal paths, and it only looked at continuity of the orientation.
Orientation, okay.
But not
so
the
because
curvature. We didn't know.
Yeah, if you consider these two clothoids and connection in the node of the lattice, you may encounter the abrupt change in the rotational velocity.
Yes.
So of course you can correct this during the steering, but there is an issue with that approach.
Yes,
I
yes,
know.
indeed. We're aware of that. I think in practice it doesn't matter that much.
Yes, I think.
But yeah, theoretically, indeed, you get this abrupt change.
But if you matter about dynamics, it may be important to take a look on it.
Yeah. Okay.
Thank you.
Good suggestion. Thank you.
Regarding the, so I understand that you assume that you know the motions of the dynamic obstacles perfectly, but I'm not sure I understand why you must assume in that case that the robot geometry is a point, or did I misunderstand that?
I didn't understand the second part of your question.
So, as far as I understand, when you consider the motions of dynamic obstacles, you also assume not just that you know those and that I understand why, but you also assume that your robot is a point. Did I get that wrong?
No.
You know,
So
you
in
said point-shaped robot in that.
Yes, in a distance-time collision space.
Yeah.
Yes.
Okay, so that's in configuration space.
Yeah.
I see. Okay. Okay.
So these shapes, these orange and green shape, already take both
I understand now.
obstacle shape and robot shape into account.
Okay, thank you.
Any other questions? If not, then I'll give the word to the next speaker.